Okay, so now I want to wrap up section 2.1. Just as a quick reminder, the link to this paper and the complete playlist that I'm making for this paper are in the description of this video. Okay, so we began section 2.1 with this mentioning of the iterative weighted least squares procedure. Then it's identical to the maximum likelihood equations. Okay, and then we saw a proof, and I wanted to first work through the proof. I got all the way to the bottom. You can view those in previous videos in the playlist. And then I'm like, okay, I proved it, but then I go back up and I'm not really seeing exactly how they're identical. So I need a little bit more work, a little more thought. Actually, I'm going to break this up into two videos. First thing I want to talk about is this maximum likelihood, is this weighted least squares. I'm going to talk a little bit more about this weighted least squares, and then in the next video we'll show how it's equivalent to basically this AB times R, okay, or AB equals R. So all this stuff up top, this is basically what we showed previously in the playlist, and so where I want to spend my time right now is really just on what is this least squares procedure, where did this come from, and then we'll show how it's equivalent, okay, in the next video. So let's start with just kind of going in memory lane. What is weighted least squares? Kind of need a reminder or refresher on that. So let's start there. What is weighted least squares? What's the idea? So we have a model, okay, and in this case they told us that they want to that we need to regress y, this modified y, onto x using this weight. Okay, so where did that come from? So we have y sub k, where k goes from 1 to n, equals our, from I equals 1 to m, this beta I x I k plus some error term k for I equals 1 to n. Okay, and you might be saying, well, hold on a second, why do you have an error term there? Because if we go back here, I'm scrolling up, section 1.3, y equals beta times x, and there's no error term. Okay, so don't freak out, because remember, this is a lowercase y. I'm not gonna lie to you, I don't like this notation, but this is what they've decided to use in this paper. It's hard because it's hard. It's hard to pick good notation here. But this is for the least squares procedure, so they're using this lowercase y, and because it's for the least squares procedure, it does have this error term here. Okay, and so I could write this using matrix notation, which I prefer matrix notation. So I'll still use lowercase y, but I'll use no subscript. Okay, and this is x times beta plus an error term. Okay, so when I use matrix notation, this y is lowercase y is an n by 1 vector. This is an n by m matrix, an m by 1 vector for beta, and then an n by 1 vector for epsilon. Okay, so the variance for epsilon sub k equals sigma squared sub k. Now that's the problem. Okay, because if you recall, in normal least squares, we like to have constant variance. It leads to some very nice results later down the line. Now you don't need constant variance to solve least squares, but you do need it in order to have some very nice properties. And so when you don't have constant variance, it's like, oh no, what are we going to do? Okay, and so this is the problem that least squares tries to address. All right, so written in matrix notation, the variance of epsilon, we would just use a diagonal matrix where the diagonals are the variances, and then the off diagonals are zeros. So we still have independence. Okay. Okay. Also note that the variance of y equals the variance of x beta plus epsilon. Now x times beta, this is it's not random, right? Remember, if I go back to my paper, it says x's, so let's see, set of independent variables in section 2.1. Let's go up to 2.1, and here we see x's are independent variates whose values are supposed to be known. So because their values are supposed to be known, they're not random. So its variance is 0, right? So the variance of x beta plus the variance of epsilon. So this is 0. So the variance of epsilon. So when you think about variance of epsilon, you can think about the variance of y. They're exactly the same thing. Okay? So what weighted least squares does to address this problem is it defines these weights, right? So it's like, okay, we got an idea. These are called the inverse variance weighted least squares. Okay, inverse variance weighted least squares has very nice properties. It gives us some very nice properties back to the situation where I had constant variance. So people like this method. And what this one does, so let's say for k, it would do, this is equal to 1 over the corresponding variance. Okay, so written in matrix notation, this would be 1 over sigma 1 squared, 1 over sigma 2 squared, all the way to 1 over sigma n squared, and then 0 in the off diagonals. Okay. All right, and I want to pause here because I want to see, hey, is that what they did? Is that what this weight is? Is it the inverse variance weighted least squares? And the answer is yes, but let's go ahead and show it. Okay, so let me actually move over here. Okay, because I want to be able to see this. So the variance of y equals the variance of capital Y plus z minus mu divided by d mu dy. Okay, now, well, actually, before I do anything, I want to actually go ahead and just distribute a little bit. So I'm going to have this is equal to the variance of y plus the variance of z divided by d mu dy minus, or no, plus, because when you take the variance of a negative, that basically gets squared, so it becomes positive as well. So variance of mu d mu dy. Okay. Oops. I messed up my parentheses there. D mu dy. Okay, so basically what I've done is I've distributed this d mu dy underneath z and underneath mu. And then I brought the variance into each piece. All right, so the variance of capital Y, well, again, I can go back to my paper, see how capital Y is defined, right? It does not, its variance, and nothing is random. It's like basically the variance of a constant, which is just 0. So that's 0. This piece here, d mu dy is also a constant, so it can be pulled out of the variance, and it would be squared, right? By properties of how you do variance, you would square it. So it's basically like a constant, so it comes out and then it gets squared. Okay, the variance of mu is not random, so its variance would be 0 as well. And then it would be divided by a number, but 0 divided by anything is just 0. Okay, so we get variance of z, which I think in our paper we've defined that to be capital V, d mu dy squared. So this is the variance of y, or in other words, I've written that as that's what sigma is. Okay, for the kth observation, right? So all of this, I guess, could have had a k subscript everywhere. Okay, if you follow that down, you would have a k subscript here and here. All right, so then the inverse of this would be the weight. So the weight, remember, is inverse weighted by the variance. So our weight would be, take the reciprocal. Which is exactly what they're proposing as their weight. So we can say, oh, okay, great. So they are using inverse variance weighted least squares. So that's what's happening there. Okay. So then what's the deal? How do you use those weights? All right, so remember that in ordinary least squares, we want to minimize the square difference between our observed value of the outcome y, right, lowercase y, minus the predicted value, which would then depend on this beta that's predicted, and then your covariates xik. Okay, so I equals 1 to m, and then we would sum from k equals 1 to n. So this is the idea behind ordinary least squares. You minimize this this square function. So what's different in weighted least squares? In weighted least squares, we have exactly the same thing, except now we're going to weight each observation by WK. Okay, so we're going to multiply each observation by WK. Now, what does that do? Well, when WK, or the weight, is high, then the variance, the corresponding variance, or let me write sigma squared, sigma k squared, is low, right? Because it's an inverse variance weight. So if W is high, then the variance must be low, and that's good, because you would want to give that observation more weight. And conversely, when WK is low, then sigma k squared is high. So when you have a very large value in the denominator there, that's going to make the weight small. So in when you're doing your weighted least squares, that observation will have less of a weight. Okay, so that's the general idea. Now we can write this in matrix notation, which I want to do. So basically, I want to minimize this function here, where I have y minus x beta transpose times w times y minus x beta. Okay, so this is exactly the same thing. This is just written using matrix notation. So instead of writing squared, I've written it twice, where it's once transposed, when it's not transposed, and then I have my matrix of weights here in the center. So you can go through and check that that's the same thing. Basically, y is a n by 1 vector, n is a n by m matrix, m by 1 for beta. So then when you take the transpose there, you'll end up with a 1 by n. A 1 by n vector. And then W is an n by n. N by n. And then here again, n by 1. N by m. M by 1. So you can see, check your matrix notation there and see that this is also a n by 1. So your n's cancel and you're left with a 1 by 1, a scalar, which is that sum. Okay, so you can see that these two things are equivalent to each other. Okay, so then in the next video, what do we need to do to solve this? We need to find the derivative and set it equal to 0, right? And then once you set that derivative equal to 0, you'll see, oh, I just noticed I forgot this little hat. Let me put that little hat there to indicate that's my estimate at beta. But once you take the derivative of this and with regards to beta, and you set it equal to 0, you'll see that basically you're going to get exactly this equation up here.